Welcome to my new lecture. This lecture is about discrete probability distributions, in which we would be looking at negative binomial distribution, geometric distribution, and Poisson distribution one by one. Previously, we have looked at the uniform distribution, binomial distribution, and the hypergeometric distribution. Binomial and hypergeometric distribution basically depend upon the success and failure, and the random variable in both the cases represents the number of successes in small n outcomes. However, in case of hypergeometric distribution, you choose a sample small n from the capital N, which is not the case in binomial distribution. In binomial distribution, you have only n trials. Now, first of all, let's look at the negative binomial distribution, right? जैसे कि आप लोगों को पहले बताया है कि बाइनोमियल डिस्ट्रीब्यूशन के केस में हमारे पास n जो होते हैं नंबर ऑफ ट्रायल्स होते हैं, p प्रोबेबिलिटी ऑफ सक्सेस होती है, और x जो रैंडम वेरिएबल है वो नंबर ऑफ सक्सेसेस को रिप्रेजेंट करता है. तो हमें नेगेटिव बाइनोमियल डिस्ट्रीब्यूशन की क्यों ज़रूरत पेश आई, ये क्वेश्चन जो है वो माइंड में आता है. तो सबसे पहले हम जो है नेगेटिव बाइनोमियल डिस्ट्रीब्यूशन की डेफिनेशन देखते हैं, फिर हम इसको डिफरेंशिएट करते हैं फ्रॉम बाइनोमियल डिस्ट्रीब्यूशन. नेगेटिव बाइनोमियल डिस्ट्रीब्यूशन इज इफ ए रिपीटेड ट्रायल trials can result in a success with probability p and a failure with probability q, which is equals to 1 minus p. Then the probability distribution of the random variable x, of the random variable x, the number of trial on which kth success occurs, right, is b. You differentiate it with the steric, right, x k p, x minus 1 combination with k minus 1, p raised to power k, q raised to power x minus k. As you can see that I have told you earlier that in case of a binomial distribution, the random variable represents the number of successes, or the and in case of a negative binomial distribution, the random variable represents the number of trials on which kth success occur. You have basically a fixed number of successes, and you want to find out the number of trials on which that success occurs. It is very helpful in different applications, this negative binomial distribution. It has got numerous applications, like if you want to determine how inefficient telephone exchange system is during busy times. Clearly in this case, trials occurring prior to a success represents a cost. If there is a high probability of attempts being required prior to making a connection, then plans should be made to redesign the system. तो इस तरह से बहुत सी जगहों पर जो है वो नेगेटिव प्रोबेबिलिटी डिस्ट्रीब्यूशन, नेगेटिव बायनॉमियल डिस्ट्रीब्यूशन यूज़ हो सकती है. जैसे कि एक अगर दो टीम्स के दरमियान 5 मैच सीरीज़ है और हम देखना चाहते हैं कि अगर एक जो है वो टीम 3 मैचेस जीत जाती है 5 में से, तो वो जो है वो सीरीज़ जीत जाएगी. तो हम ये देख सकते हैं कि कितने जो है दफ़ा कितने मैचेस में वो क्या प्रोबेबिलिटी है कि वो टीम जो है वो विन कर जाएगी. लेट्स से इन 4 मैचेस, इन 5 मैचेस, इन 3 मैचेस कि वो सीरीज़ जीत जाए. तो इस तरह जिसमें हम नंबर ऑफ़ ट्रायल्स को रेंडम ले रहे हैं, तो वहाँ पर जो है हम नेगेटिव बायनॉमियल डिस्ट्रीब्यूशन यूज़ कर सकते हैं. अब नेक्स्ट जो है हम इसी की एक एक्सटेंशन कह लें या फर्दर एक डिस्ट्रीब्यूशन है जिसे हम ज्योमेट्रिक डिस्ट्रीब्यूशन कह रहे हैं. ज्योमेट्रिक डिस्ट्रीब्यूशन, इसमें नेगेटिव बायनॉमियल के केस में जो रैंडम वेरिएबल है वो नंबर ऑफ ट्रायल्स को रिप्रेजेंट कर रहा है, राइट, ऑन केथ सक्सेस. अगर k इज इक्वल टू 1 हो जाए तो वो कौन सी डिस्ट्रीब्यूशन बन जाएगी? ज्योमेट्रिक डिस्ट्रीब्यूशन. The number of trials on which first success occurs is basically a geometric distribution. Formally हम इसे कैसे दे सकते हैं? If repeated independent trials, if repeated independent trials can result in success with probability P and a failure with probability Q, right, where Q is equals to 1 minus P, right, then the probability distribution, then the probability distribution of the random variable x, of the random variable x, the number of trials on which first success occurs. Simply you have to find out the number of trials on which first success occurs, right? Then it is given by g of x p is p into q raised to power x minus 1. Just consider the case that you are giving driving test for getting the driving license. The number of trials on which you get the driving license is basically sort of a geometric distribution. Similarly, you can model a lot of different situations in which basically you have number of trials for the first success, right? And negative binomial is the case, the number of trials for k successes, and k is greater than 1 in that case. And for the case of geometric, you have that k is equal to 1. You can also put this k is equal to 1 in this formula, right? And you can get the same result for it, right? Now the as I have given you the values of mean and variance for different distribution, the mean for this geometric distribution is given as 1 over the probability of success, and variance for this is given as 1 minus p over p square, or you can say as q over p square, right? These are the mean and variance for the geometric random variable, right? Next we would be looking at the Poisson distribution, right? Which is given by Poisson random variable, right? And first we would be looking at the Poisson process and what are different properties associated with the Poisson process, right? In case of a Poisson process, you find the number of outcomes occurring during a given time interval or in a specified region, right? Poisson, the number of outcomes occurring in a specified region, right, or during a given time interval or Poisson एक्सपेरिमेंट्स, राइट? जब हम किसी एक स्पेसिफाइड टाइम इंटरवल या स्पेसिफाइड रीजन कुड बी एरिया, इट कुड बी लेंथ, इट कुड बी वॉल्यूम, तो हम जब एक स्पेसिफाइड रीजन या स्पेसिफाइड टाइम के या एक टाइम इंटरवल के अंदर प्रोबेबिलिटी फाइंड आउट करना चाहते हैं किसी रैंडम वेरिएबल की, तो वो पॉसॉन एक्सपेरिमेंट कहलाता है। अब हम इसकी डिफरेंट प्रॉपर्टीज़ देखते हैं कि कौन सी प्रॉपर्टीज़ जो हैं वो पॉसॉन प्रोसेस बनाते हैं, राइट? प्रॉपर्टीज़ ऑफ पॉसॉन प्रोसेस। First is that Poisson process is memoryless, right? By memoryless we mean the number of outcomes occurring in one time interval or specified region of space is independent of the number that occur in any other disjoint time interval or region. इसका मेमोरीलेस का मतलब ये है कि एक अगर जो स्पेसिफाइड रीजन या स्पेसिफाइड टाइम इंटरवल के अंदर जो आपकी प्रोबेबिलिटी आ रही है या जो आउटकम्स आ रहे हैं वो इंडिपेंडेंट हैं किसी भी और रीजन या किसी भी और टाइम इंटरवल के अंदर। लेट्स से अगर मैं कहूँ कि ये मेरे पास एक डिस्ट्रीब्यूशन है लाइक दिस, राइट? दिस इज़ माय डिस्ट्रीब्यूशन, ये डिफरेंट डिस्ट्रिक्ट। अब अगर मैं इस रीजन की बात करूं, राइट, तो इस रीजन के अंदर जो प्रोबेबिलिटी है दैट इज इंडिपेंडेंट कि इस रीजन के अंदर क्या प्रोबेबिलिटीज हैं, राइट? यू कैन इन ए रफ वे यू कैन अंडरस्टैंड इट लाइक दिस, राइट? कि इस रीजन के अंदर जो प्रोबेबिलिटी है या जो आउटकम्स हैं वो किसी भी और रीजन जो इससे बाहर है वो उससे इंडिपेंडेंट है। दिस इज मेमोरीलेसनेस, राइट? Next is the probability that a single outcome will occur in a given small time interval or region is proportional to the length of time interval और रीजन कि एक आउटकम की किसी स्पेसिफाइड रीजन या किसी छोटे से रीजन या किसी टाइम इंटरवल में आने की प्रोबेबिलिटी डिपेंड करता है कि उसका इंटरवल कितना है, राइट? और ये उससे बाहर किसी भी आउटकम्स के ऊपर डिपेंड नहीं करती, राइट? दिस इज द सेकंड इम्पोर्टेंट प्रॉपर्टी ऑफ दिस Poisson process, right? कि किसी specified region या किसी टाइम इंटरवल के अंदर किसी आउटकम के अकर करने की प्रोबेबिलिटी जो है वो उसके टाइम इंटरवल की लेंथ या उस रीजन के ऊपर डिपेंडेंट होती है, वो उससे आउटसाइड किसी चीज़ पर डिपेंडेंट नहीं होती. थर्ड वन, the probability that more than one outcome will occur in a short time interval or fall in such small region is negligible, right? कि एक छोटे से टाइम इंटरवल के अंदर जो है वो एक से ज़्यादा आउटकम्स की जो प्रोबेबिलिटी है वो ज़ीरो होती है, निग्लिजिबल होती है, या एक छोटे से रीजन के अंदर एक से ज़्यादा आउटकम्स की प्रोबेबिलिटी जो है ज़ीरो होती है. ये सारी प्रॉपर्टीज जो हैं वो उसे पॉइसन प्रोसेस बनाती है. अब हम जो है फॉर्मली इसकी डेफिनेशन की तरफ चलते हैं. अब हम पॉइसन डिस्ट्रीब्यूशन की तरफ चलते हैं. इट इज़ डिफाइंड एज द प्रोबेबिलिटी distribution of the Poisson random variable, right, x representing the number of outcomes in a given time interval or specified region denoted by T is, right, this T is the specified region or time interval. You should not confuse this T only with time. It could be time, it could be length, it could be area, it could be volume, right? So in this case the probability of the random variable x lambda t is e raised to power minus lambda t, right? Lambda t raised to power x over x factorial, right, where x could be 0, 1, 2 up to so on, right? This lambda is basically average number of outcomes per unit. It could be time, right, it could be distance, right, it could be area, or it could be volume, right? And e is that exponent, right, which has got value 2.718, right? Now you can use this formula, and if you are interested in finding the Poisson distribution sums, then it is given by probability of r lambda t summation x from 0 to r, right, probability of x lambda t, right? So you can find these values, and the mean of this is given as lambda t, mean of this Poisson distribution is lambda t, and variance of the Poisson distribution is also lambda t, right? So the mean and the variance of the Poisson distribution are lambda t. So you can also do some mathematics with it, that if you are given the average or the mean, then you can amend this formula A as, right, say this is formula A then could be is given as, right. I am not going to the next page because it's better to resolve this Poisson distribution over here. A could be written as, then probability of this this is x, and then this lambda t becomes mu, and this would be e raised to power minus mu, right, mu raised to power x over x factorial, right. So this is, I know that this mu is equals to lambda t, then I can substitute this mu by lambda t. So we have come to a very important result, that if mu is equals to lambda t is the average number of outcomes, then you can amend this formula of Poisson distribution by x mu e raised to power minus mu raised to power x over x factorial, right. This could be useful in solving the problems. Now we can Poisson distribution has a lot of applications in different field. You can search in any book, right, and we can go to make a very useful basically relationship between binomial and Poisson distribution. When you have the probability of success is very low, let's say it approaches to 0, and the number of trials are very large, right, then we can approximate basically the binomial distribution with the Poisson distribution. Let's see how in the next section, which is approximation of binomial distribution by a Poisson distribution. Right? Approximation of the binomial distribution by a Poisson distribution. Let x be a binomial random variable with probability distribution b of x and p. This is, remember, this is the binomial distribution when the number of trials are very large. This n tends to infinity, probability of success tends to 0 as I told earlier, and then this np, if this n tends to infinity, is mu, right, mu, such that this mu remains constant, right. Then basically you can say that b of x n p when this n tends to infinity is p of x mu. So when you have large n and very small p, right, then you can approximate your binomial distribution with the Poisson distribution, right, with the parameters such that mu would be equals to np, right, and x is the random variable that represents the number of successes, right. This is how you can approximate your binomial distribution by Poisson distribution, and it's a very important result in case of the relationship between different distributions. Now let us look at some numerical problems, right, to give a more clear understanding about these concepts. Okay, this is the first numerical. A scientist inoculates mice one at a time with a disease germ until he finds two that have contracted the disease. If the probability of contracting the disease is 1 by 6, what is the probability that 8 mice are required? If you closely look at this statement of this problem, that the number of successes are fixed, that you have to find basically two that have contracted the disease. So k is equals to 2 in this case, right? And the probability of contracting the disease is 1 by 6, right? And next is, what is the probability that 8 mice are required, right? You basically are interested in the number of trials, right? The number of mice that are basically tested for the germ, right? So this looks like a negative binomial distribution with x is equals to 8, right? So you have to find basically b steric of x is 8, right? K is 2, right? And p is 1 by 6. You just need to put this in the formula, right, which would be x minus 1, that is 8 minus 1 over k minus 1, that is 2 minus 1, p raised to power k, and q, which is actually 1 minus p, so 1 over 1 minus 6 is 5 by 6, so it should be 5 by 6 raised to power this x minus k, which means 8 minus 2. So you can solve all this stuff using your calculator and get the result. Now let's see the next numerical. The probability that a student pilot passes the written test for a private pilot's license is 0.7. Find the probability that a given student will pass the test on the third try before the fourth try. So now if you look at it, it looks like a geometric distribution, because you have to find the number of trials for the first success when the student will get the license, right? So in the part A, you have to find out this g of x is the number of trial is 3 and the probability of success is 0.7. So it should be p is 0.7, q is 0.3 raised to power is x minus 1, I believe, so it should be 3 minus 1. So you can easily find this out using this formula, right? Now for the second part, before you are interested in probability of x less than 4, so it should be summation x from 1 to 3. It cannot be 0 to 3 because there is 0 is not a try, right? It should be 1, 2 and 3 tries, g of x and 0.7. So you have to sum basically 0.7 into 0.3 raised to power, first it would be 1 minus 1 is 0, In case second is 0.7 into 0.3 raised to power uh, 2 minus 1 is 1 plus uh, 0.7 into 0.3 raised to power 2, right? You have to get all these values and sum them out, you will get the result. So in our next numerical, a certain area of eastern United States is on average hit by 6 hurricanes a year. Find the probability that in a given year that area will be hit by fewer than 4 hurricanes and anywhere from 6 to 8 hurricanes, right? This looked like a Poisson distribution, right? Because we have to find the probability in a certain region in a certain time, right? In a year, right? So in the part A, we are interested in probability of x less than 4, right? So here the average hurricanes a year, that is mu, is equals to lambda t is 6, right? So we are given this, we have for this we have to sum basically from 0 to 3, right? Probability of x, and this mu is 6, so it should be summation. You can solve it by using the formula like this: summation x from 0 to 3 uh, e raised to power minus 6, and this 6 raised to power x over x factorial. There is another way. There is a table A2 in your book. You can find the result for this summation in that table as well, right? In the next case, you are interested in finding the probability of x uh, from 6 to 8. You can solve it by summation x from 6 to 8, probability of x 6, right? This is one of the way. If you are interested in finding out using the table A2, then basically you have to start the sum from 0. So it would be summation x from 0 to 8, probability of x 6, minus summation x from 0 to 6, probability of x. So this would give the same result as this one, right? So you can solve it out like this by any means as you like. The next numerical is average number of mice per acre in a 5-acre wheat field is estimated to be 12. Find the probability that fewer than 7 mice are found on a given acre on 2 of the next 3 acres inspected. So once again we have to find the probability of the random variable in a specified region. So it's a Poisson distribution with mu is 12, right? It is given as 12 per acre, right? And we have to find out this probability of x less than 7, right? So it should be sum of x from 0 to 6, right? Probability of x and mu is 12, right? You can see the result from the table A2 in the Walpole book, right? Or solving it, the sum of these 7 terms would be let's say a bit lengthy, so using the table is fine in this case. In the second part, you want to find the probability that fewer than 7 are found on 2 of the next 3 acres inspected, right? So you can use the binomial distribution for this one because that either you should use the binomial distribution. In this case, for part B, this is part A. For part B, it would be B of x is on 2 of the next, right? It should be 2, and n is 3, and you need to find out this probability of success. This mu is given as np, right? np or lambda t. You can find this p from here and substitute its value down here, and you will get the result, right? I am leaving this to you people as an exercise, right? And I would like to see your results in the comments box, right? I hope you have understood different distributions like the negative binomial and geometric distribution, which basically in which the random variable represents the number of trials, right? For the negative binomial it is k successes, and for the case of geometric distribution it's for the first success. And in case of a Poisson process, the random variable represents the probability in a given time interval or in a specified region. By region we mean it could be a distance length, or it could be an area, or it could be an volume, right? Thank you all for your time. See you again.